Okay, so last time we looked at kind of a general overview of sequences, and we kind of did some observational explicit formula writing where we looked at what was happening from one term to the next, and we kind of related it to the index of the term, and then we wrote a general formula using that observational technique. Now we're going to, in 8.2 and 8.3, we're going to look at specific types of sequences, and we're going to have formulas for how to write explicit formulas depending on what type of sequence it is. First one we have is an arithmetic sequence, which we saw examples of last time. We just didn't call them arithmetic sequences. They're essentially sequences that have a common difference, meaning the difference between any two consecutive terms is constant. So you can think of these as sequences where you add something to a term to get to the next term, right? Um, the So, for example, we look at these examples here. This one looks like we go from one term to the next by multiplying by 2, which means it's not a arithmetic sequence. You can say no on this one because we go times 2 to get from one term to the next. Whereas in part B, the thing that happens from one term to the next is a plus 4 pattern, right? We add 4 to get from one term to the next, which means yes. And then it asks us to find that common difference, meaning we're going to take any term and subtract the term before it to find the difference between any two consecutive terms. So if I take the term 13 and subtract 9 from it, I get that common difference of positive 4. Now, you want to do it in the correct order because the common difference can actually be a negative value if your sequence is decreasing as you go further and further into the terms. So you always want to do a term minus the previous term. All right, so that's how we find the common difference. Now, if we have the common difference and we have the first term, such as this example here, we can just start writing the terms because we know what the first term is. A1 is 17, which means my first term is 17. And then my next term will follow by adding the common difference to the first term. So when I add negative 3 to 17, I will find the next term of 14, and so on. So if I add negative 3 again to that, that gives me 11. Adding negative 3, continuing to add negative 3 over and over again, we get the first 5 terms, and then we can say dot, dot, dot to continue on the sequence. Okay, so knowing the first term and the common difference gives us a way to get from one term to another. In the next example here, we know that the first term is 8, and then we're missing some terms. So this is A1, which is my first term. A2 is missing. A3 is also missing. We don't know A3, but we know A4, which is an interesting situation because while we don't know, we're skipping a few terms here, we know 2 specific terms. So we can actually find those missing terms and find the common difference here by just knowing 2 terms. Now, to go from A1 to A4, we're adding the common difference, right? We go from A1 to A2, we add the common difference D. So to go from A1 to A2, we do A plus D. To go from A2 to A3, we do A plus D. We go from A3 to A4, we do A plus D. So if I wanted to skip all of that to go from A1 to A4, how many times am I adding that common difference?
Three times.
3 times, thank you. So we're adding 3 times D to go from A1 to A4. So we can actually write a formula to solve. We can say 8 plus 3 times the common difference gives me 14. Right? In such a small example, it may be easy to just guess what D is. Like, oh, if I add 2 every time, does it get me to 14? And it probably does. So it's not super hard to guess in these situations. But if the numbers are weirder, if you have fractions, for example, for A1 and A4, you don't really want to try to guess what the fraction you're adding, or if D is a fraction, for example, you don't want to try to guess it. So it's better to just come up with this formula by saying, okay, I'm adding 3 times because the index goes up by 3, so we must have added the common difference 3 times, and then we can solve for this D. We can subtract 8 from both sides, 3D equals 6, and so therefore D equals 2. So then if D is equal to 2, we can actually fill in the missing terms, right? The missing terms being, we add 2 every time, so 10, 12, 14, and then finally the question was asking for A5, which is the next term, which would be 16. Right, that's A5. Right, so we can deal with knowing the common difference or not knowing the common difference, but as long as we're given 2 terms, we can find the common difference by figuring out how many times D is being added and then using that formula. Next, we're going to talk about the explicit formula for an arithmetic sequence, which is given here. I'm not going to go over how to derive that, but we're given a formula for the explicit formula for an arithmetic sequence. So if you recognize the sequence as being arithmetic, you can automatically assume that this formula follows. A sub n being the nth term of the sequence, A sub 1 being the first, and then D being the common difference. So if I know, let me see if there's an example, like write an explicit formula for the sequence. I think those are fine. Let me do one of these. We have a sequence given here. We are told that it is a arithmetic sequence, and we want to write an explicit formula. So all we need for this explicit formula is to figure out what A1 is and what D is, and then we can write the formula for A sub n. So A1 is the first term, which in this case is 6, and D is the difference, common difference between any two terms. So if I take any term like 16 and I subtract 11, that gives me 5, which means the common difference is 5. Or you can say, oh, okay, from one term to the next, I do a plus 5, so then the common difference is 5. And then we can write the formula for an by just following the formula at the top of the page here, which will be the first term, which is 6, plus D, which is 5, times n minus 1. Now, for ease of use, I would recommend distributing this 5 and simplifying a little bit, just so we have a linear equation of the form y equals mx plus b, something that looks like that. So if I distribute that 5, I get 6 plus 5n minus 5, and then we can combine the 6 and the minus 5 and write our explicit formula as 5n plus 1. Right, and that is a linear formula, which I kind of alluded to last time. Arithmetic sequences, if you're increasing by a specific number every time, that's going to be the slope, and you're going to end up with some kind of linear equation for the explicit formula. Are there any questions so far? Okay, let us move on. You guys can figure those out. Oh, interesting. There's no questions. Maybe I'll pull up the worksheet because there's a question type that is not really on here. I think that is on the worksheet. Oh, I guess not. Actually, never mind. There's not that question type. Okay, let us move on to geometric sequences. So arithmetic sequences increase by a common difference every time, whereas geometric series are going to have this thing called the common ratio, which means to get from one term to the next, we're multiplying by something, right? This was like that example that we said no to up in the first couple of examples. This one here, we said this was not this was not arithmetic. It did not have a common difference because we were multiplying by 2 to get from one term to the next. That's actually called a geometric sequence. So geometric means there's a common ratio that we're multiplying by every time, and we find that common ratio by dividing a term by a previous term. So these this first sequence here is geometric, yes, because we're multiplying by 2 to get from one term to the next. But if you can't tell, like this one's easy to tell because I could say, oh, I know I go from 1 to 2 by multiplying by 2, from 2 to 4 by multiplying by 2. But if they're weird fractions or decimals and you can't quite tell if you are multiplying by the same thing over and over again, you have to take terms and divide them by the previous term. So you have to look at 2 divided by 1. Okay, that gives me 2. I have to look at 4 divided by 2. Okay, that also gives me 2. And then we look at 8 divided by 4. Okay, that's also 2. So now I'm pretty sure this is geometric. We'll just check 16 divided by 8, and that's also 2. So then my common ratio R is going to be 2. Okay, I'm only showing this because you may have to do it when it's not super obvious and you can't really tell that it is a geometric sequence. You may have to divide terms by previous terms to check if you're getting the same ratio over and over again, which is called a common ratio. Listing terms of a geometric sequence, we can do this just like we did the arithmetic one, except now when we start with the first term, to get to the next term, we're going to multiply by the common ratio and not add it, right? In arithmetic sequences, we were adding the same thing over and over again to get terms. Now we're going to multiply by the common ratio. You guys can figure that one out. Let me go over this one because this is kind of like the previous example. But if I have 3 as my first term, so that's A1, and then I'm missing a couple terms again. I'm missing the A2 and the A3, and then I have A4. So A2, A3, A4, A2 and A3 are missing. A4 is 24. So we can do the same thing we did last time to get from here to here. We multiply by D every step of the way. So to get from A1 to A4 directly, we would multiply by, what would I multiply by to get from A1 to A4?
By 8?
No, I mean in terms of D.
Oh.
So we can set up the equation. What does multiplying by D 3 times equate to as a single product?
D cubed?
D cubed, good. Because we're multiplying by D and then D again and then D again. So we're actually multiplying by d 3 times. So that's actually times d cubed. So the formula that we set up here would be we start with 3 and we multiply by d cubed and we end up at 24. And then we're going to solve that. So d cubed, when we divide by 3, is going to end up being 8. And like Brian was saying, d is going to end up being 2 because we cube root both sides. And so if d is 2, then we can start filling in some of these gaps, right? 3 times 2 is going to be 6. 6 times 2 is going to be 12. And then 12 times 2 is going to be 24. And the question is actually asking for a sub 2, which is the second term. So we can box that answer for 6. We can write it on the side here as well. A sub 2 is equal to 6. All right, and then finally, I don't think the video went over this, but I'm going to go over the explicit formula for a geometric sequence as well, given here. It kind of makes sense to do the arithmetic and geometric in the same day. To find any term, to find the nth term of a geometric sequence, all we do is take the first term, multiply by the common ratio raised to the n minus 1 power. So if I were to try to write the formula for any given arithmetic sequence, let me actually do part B here. So all we need to do is find A1 and R. Right? A1 is the first term. That's easy. That's -1 given to me. R is the thing that we're multiplying by to get from one term to the next. If it's not easy to just look at it and tell what R is, you may have to go to the side and say, okay, I'm going to take a term and divide by the previous term. That gives me -3. This also works if I do the -9 divided by 3. I also get -3. Or if I take the next term, well, I guess I don't have the next term, but we see that the common ratio is going to be -3 in this sequence. So we're multiplying by, or times -3 to get from one term to the next. And so our formula, a sub n, is going to be start with the first term, a1, which is -1, times the common ratio, which is -3, raised to the n minus 1 power. And we don't really have any way of simplifying that. I guess we do a little bit, but I would just leave it like that. We could split this into a fraction and then maybe combine it with the -1. But I think that's fine as far as the formula goes. So the type of question that could come up is like a follow-up example to this would be like find the sixth term in this sequence. And so if you have an explicit formula, you don't have to continue from this term and multiply by -3 every time. We can just plug in 6 as for our n and say, okay, well, a sub 6 will be -1 times -3 to the 6 minus 1. So n becomes 6. And so a sub 6 equals a -1 times -3 to the 5th. And then -1 times -3 to the 5th. Oh, what's -3 to the 5th? 3 times 3 is 9. 9 times 9 is 81. 81 times 81 times 3. Nope. No, not 81 times 81. Sorry, it's 243. Oh, that took me so long. So the sixth term in the sequence would be 243. And then another follow-up question. So this is a follow-up question. Another follow-up question could say, how many terms are in this sequence that's given to us. How many terms are in this sequence? Now, notice that this sequence stops. So it's a finite sequence, right? The question also says finite geometric sequence. So the question could be how many terms are in this sequence, and we have a stopping point. So what we would do is we would take our stopping point and set it as our nth term and figure out what n is. That would be the number of term that this is, right? Because the first term here is called A1, the second term is called A2, the third term is called A3, and so on. We want to know what numbered term that 2187 is. So we can take that 2187. Let me actually move these up a little bit. We can take that 2187 and set it equal to our formula, -1 times -3 to the n minus 1, and solve for n. And n will be the number index of this term. So divide both sides by -1, so negative 2187 equals -3 to the n minus 1. And then we want to solve for n. So any ideas what we can do to get this n isolated? What would be the next step?
Take the log or natural log of both sides.
Yeah, take the log of both sides. Now, I know that we're multiplying by 3 every time, and we started with 1. So these are all going to be powers of 3, right? So while I could just take a natural log or a standard log of both sides, what I could do is I know that this is a power of 3 as well, right? So if I write this as a power of 3, then I know that my exponents have to match up, right? Taking a log of both sides also works, but I'm actually going to rewrite this side as a -3. Actually, no, that would be dumb, because then why wouldn't I just know what this power is? Let's take the log of both sides. And let's use natural log, because I like that idea. So if I throw a natural log onto both sides, I get a natural log of -2187. That's fine. And then the exponent will come to the front, n minus 1 times natural log of -3. We're going to distribute this natural log of -3 into this parenthesis here. Oh no, let's not even do that. You know what? We can't do that because you can't take you can't take logs of negative numbers. So the calculator, if you try to do that, would give you an error. So we do have to rewrite this as a power of -3 and then solve from there. So we have to figure out what power that is. 243 was the 5th power. 6th power would be 600 something. 7th power would probably work for this. So this is going to be -3 to the 7th equals -3 to the n minus 1. And so if you write both sides with the same base, then you can say that the exponents must be equal to each other. So I have that 7 equals n minus 1. And so adding 1 to both sides would mean that n is equal to 8. So this is this sequence has 8 terms. Right, so I did a couple of extra examples here because you may see questions like that on the worksheet or the homework. And that concludes 8.3.